different observational aspect of the Orion star-forming complex. Well, sadly, I cannot be there with you to celebrate in person the enormous contribution of Lee to the field of star and planet formation. This work I did with the collaboration of several groups, the ARISO group, Activity and Rotation of Young Stellar Objects, the Modela group is Models and Observation of this Evolution in Latin America, the local group here in UNAM and Ensenada, and the SIDLAB Quad group that is a CONACYT project that was approved last year. So I want to remark first that Lee is one of the most influential people in my academic life. It was a real pleasure to be at CFA with Lee as a graduate student, and I was honored to work with Lee and Nuria as a postdoc in Michigan. Well, this is my outline of my talk, and I want to start with a general description of the Orion star-forming region. So the Orion star-forming region has two main obvious stellar associations. One is located in the head of Orion, the Lambda Orionis cluster, and the other is located to the south, the Orion OB1 association, which includes several sub-associations with different edges, as you can see in this plot. Particularly in the Lambda Ori region, the ring of dust and gas and the stellar Hubble-like expansion obtained from proper motion by Marina Kunkel suggests that a supernovae explosion formed this region. An alternative scenario of star formation for the Lambda Orionis region that includes gravitational feedback as a young cluster dispersal mechanism is in the Manuel Zamora's work in 2019. So if we look this region in more detail, we can see several clusters and stellar concentration of different evolutionary stages. In a classical view, these stellar groups occupy different regions on the sky. However, in the last year with Gaia data analysis, we know that we can find different stellar populations in the same field of view. As you can see in the distant distribution of the subassociation Orion OB1b provided by Cesar, and also in this plot from Marina Kunkel, in which we can see that if we are looking in the same region in variation declination, we can have different stellar population located at different distances. A specific example I want to show you, the Epsilon Ori region. So here I select a primitive sequence star in a region of 1 degree radius, centered at Epsilon Ori. And in this plot, you can see 4 different groups with different proper motion. And also, if we plot the histogram in distance of these 4 groups, you can see that also are located at different distances. What about the spatial distribution? So if we see the spatial distribution, the 4 groups are everywhere in the region. So there is no special location on the sky for each star cluster. So see next talk by Marina Kunkel for additional information about the kinematic and dynamic of young stellar population. Um, so the key takeaways here is that we need to consider that in the same line of view, we can have different stellar populations that need to be analyzed individually. For example, to obtain general properties as distances and ages. So I want to show you now the observation that we have. Um, we have compiled an extensive database of low resolution optical spectra in this complex using different facilities for many years. Also, we have available the near-infrared high-resolution database provided by Apogee Survey of Sloan. Partial result of this, based on this data set, is in Cesar's work, myself also, Ezequiel Manso, Marina Kunkel, and one paper in preparation by Carlos Roman. So we also have light curve in this region. We extracted and analyzed test light curve for stars, looking for mainly periodic stars. In the standard configuration, test provides photometry every 30 minutes for about 27 days. In a paper that were recently accepted, my student Javier Serna provides rotational period of a star in the Orion complex based on this data set. Also, we have compiled rotational periods from previous work. So the stellar characterization started at the beginning of my journal at CFA, where with the advising of Lee, Luria, and Cesar, I started to perform a spectroscopic characterization of Herbig AB stars and T-Tauri stars, which is the basis of this tool, the SPT class tool. So we use this tool to analyze the low resolution spectrum and obtain spectral types, measurements of lithium to confirm youth, and measurements of H alpha to estimate the accretion status of the stars. For example, in this plot, we can see the equivalent width of lithium versus effective temperature, given the spectral types. For the Orion OB1 association, and we have here a comparison with the Pleiades. Another example of this kind of analysis is the analysis of a Lamos field in the Orion OB1b association performed by Luisa Zamudio in her undergraduate thesis presented 2 weeks ago. Here we can see the separation between classical and weak T-Tauri star using the method proposed by Cesar, based on the spectral type and the equivalent width of H alpha. We can separate classical and weak, and we can also obtain classical weak T-Tauri star that is a class in the middle between classical and weak. Here you can also see the location of the bona fide T-Tauri stars selected not only that have lithium in absorption, but also have a proper motion and parallax coherent with the region. And of course, the Gaia, the parallax and proper motion are from Gaia EDR3. In the high resolution analysis, we have several tools for analyze apogee spectrum and obtain effective temperature, surface gravity, metallicity, radial velocity, projected rotational velocity. Of particular interest is the radial velocity to perform a six-dimensional space velocity analysis of a stellar population. And also the rotational projected velocity is important to perform studies about angular momentum evolution. Once we have spectral types or effective temperature, we can use the massage tool to obtain stellar ages and masses. In brief, the massage tool estimates visual extinction by comparing the observer Gaia to mass color with the expected color from Luhmann's 2020. We estimate the stellar luminosity using the Gaia parallax and the volumetric correction from Picard and Mamayev, or from the work from Kenyon and Harvard. Once we locate the star on the edge diagram, we obtain stellar masses and ages by comparing with a chosen evolutionary model. So far, massage include these evolutionary models that are in this presentation. We implement a Monte Carlo uncertainties propagation method to obtain error bar in the estimated parameter. Here, I show you an example of the distribution of possible results for one star. From these distributions, we can estimate the most probable value and its uncertainty, in the sense that we can estimate the visual extinction, the luminosity, stellar age, and stellar masses with its uncertainties. So be aware that the results here are model dependent. For example, here I compare the masses and ages from two standard models, Parsec and MIST. In general, Parsec give older ages than MIST for a star of 1 solar masses or less, as you can see in this plot here. But if we consider a non-standard model, that from Summers, and the models from Summer include a stellar spot with different surface coverage. And we can see that models with more extensive stellar spot coverage will give us more massive stars. In the x-axis is no spot case, and in the y-axis is different spot coverage. If we compare the age, so the more extensive stellar spot coverage will give us older stellar ages too. Okay, so the key takeaways here is that we need to consider the model dependent in the derivation of stellar ages and masses, in which the effect can be different depending on the stellar masses. This is a difficult problem since stars in the same young stellar population can have different rotations and magnetic fields, that affect the location on the HR diagram. Uh, but well, in the evolutionary study, assuming that we can have similar systematic from an evolutionary model, we can recommend using a limit range of effective temperature and a unique evolutionary model to derive stellar masses and data. So it's basically the differential, have differential ages in using a single evolutionary model. So now I want to move to the rotation field. Lee has contributed for more than 35 years in this field, in this rotational activity. Particularly in this paper, this John Stoffer already indicates that the angular momentum lost in the early stages must be very efficient. So we have some works in this field too. For example, my student Javier Serna implement two tools to study stellar rotation. The first one is the test extractor tool, which performs a basic analysis of test light curve and estimate rotational periods using the long-scalar method. Also, the light curve are used in two PhD projects to study stellar activity based on different detection and analysis, and to study the morphology of light curve using machine learning techniques. The other tool is this one is to obtain the projected rotational velocity using Fourier transform method, which doesn't require the use of spectroscopic templates. So using this kind of method of measurements, we can study the evolution of stellar rotation as in CERNA 2021. So we can see this rotational velocity evolution, in this case of T Tauri star in the Orion star-forming complex. And the solid line shows the median value in each beam, and the shadow region show or include 50% of the entire sample. The observed trend followed a general trend similar to the Gallet and Bouvier models that are the dashed line here. This model include the angular, assume that the angular velocity is constant during the first million years when this is present. This is in agreement with the existence of an efficient angular momentum loss mechanism. After that this disappeared, the BC9 tend to increase due to a stellar contraction and angular momentum conservation. Now I want to show you several distributions of BC9, splitting in several classes of accretor. Here is the for classical T Tauri, for weak T Tauri, and for classical weak T Tauri. So you can see here that the classical T Tauri mostly are located below the dashed line that separate the fast rotator from the slow rotator. So in general, classical T-Tauri star have smaller rotational velocity than weak T-Tauri star, supporting the scenario in which the activity in this regulates the angular momentum during the first million years. The number here in this plot are the fraction of fast rotator for the entire sample and the sample in which we remove the the binaries and the probable binaries. Now, I like to talk about stellar rotation and the multiple stellar population detected in the Orion Nebula Cluster by Beccari in 2017. And also, after analyzing the non-binary distribution, Teresa Gerakova claims that the three populations observed in this region correspond to three separate episodes of star formation in the US. So I am using the same photometry provided by Giacomo Beccari to test an alternative explanation based on stellar rotation. First, we select kinematic members based on the distribution in parallax and proper motion modulus. And then we cross-correlate with the compilation of rotational period that Javier Serna did in this lesson, in this work. So here is a similar plot as here, the original paper in Beccari. And we split this in two groups. The main groups is the group 1 and the red group is the group 2. The size here is the inverse of the rotational period. As you can see in this distribution, the group 2 rotate faster than the group 1. So we know that a single stellar population can have both slow and rapid rotators. And also, we know that magnetic fields and stellar rotation can affect the observed color and the luminosity, particularly the magnetic field and stellar rotation could produce redder colors. So stellar rotation, in this way, stellar rotation is a reliable alternative explanation for the different stellar population observed in the Orion Nebula Cluster. Also, one problem is that the ONC must have also an unresolved binary. So some of these stars in this group must be also an unresolved binary. So here we need actually additional complementary study of stellar multiplicity and stellar rotation to clarify the origin of the stellar populations observed in the Orion Nebula Cluster. Now, this is a preliminary result of stellar activity. My student Maria Batista uses the calcium line as indicator of stellar activity. Following this scheme, the equivalent width of the H and K lines is converted to the activity indicator. So here we show you this activity indicator versus stellar masses for weak T-Tauri star and field star. recognized because these field stars don't have lithium in absorption as the weak Itauri stars. So it's apparent that weak Itauri stars are more active than field stars. And also here, as expected, the older field stars show less stellar activity in comparison with younger T-Tauri stars and follow the expected sequence of the evolution of the stellar activity. The key takeaways here is that this Sinai evolution suggests a mechanism that extracts angular momentum from the stars when the disk is present. Classical T-Tauri stars have a smaller rotational velocity than weak T-Tauri stars, supporting the scenario in which the accreting disk regulates the angular momentum of these varying stars.
You have 5 minutes left.
Okay. The stellar rotation effect is a reliable explanation for the multiple stellar population observed in the Orion Sea that is not necessary to claim different episodic of star formation. As expected, the Tauri stars are more active than field stars. My final point here in the 5 minutes is the morphological classification using machine learning to classify a test-like curve of joint stellar objects. Here, you can see the 11 classes that we are using. For example, this class has a single period. This row here have classes that could have a multiple periods, including the eclipse in binary, because we can have the periodicity here and also the eclipse in the light group. Also, we have the dippers, regular, and the noisy, but the noisy also could be a not variable star. We are testing 28 features from the brightness histogram, light curve, or periodograms to identify the 11 morphological classes by using machine learning techniques. As an example, here in this plot, I show you a three-dimensional feature space in which we can separate several classes. For example, periodic, noisy periodic, not variable, and dipper. In particular, interest is the dippers because the variability in this class is regulated by a variable extinction produced when an overdensity of dust in the disk crosses the line of view. And indeed, in this colored diagram, the dipper class shows systematically more near-infrared excesses than periodical classes, linking the dipper class with the presence of a protoplanetary disk. For more information about stellar variability in joint stellar objects, see the talk by Lynn Hillenbrand and by Greg Herzog on Thursday. So finally, the basic idea in these works is to confirm the membership and youth of the joint stellar populations, characterizing their disk, stellar rotation, and stellar activity, and thus we can study the interplay between angular momentum, stellar activity, protoplanetary disk in joint stellar objects with different masses and ages using a large database. So this is my last slide. I just want to say thanks, Lee, for all your contribution and teaching. Thanks.
Thanks a lot, Jesus. Do we have questions in the audience? Yes, Patrick and Belle.
Thanks for the nice talk. I wonder whether in your different population you see a different fraction of the WTS over CTS numbers. So do you see variation of those classes from one population to another?
Do you mean in here?
Yes, in the different population you studied. If you just compute the ratio of WTTS over CTTS, yeah, would you see variations from one population to another?
And well, I see actually variation in one population and another is a similar result that Cesar Briceño presented yesterday, in which different stellar population with different ages have a different fraction of classical Titari star. I don't know if this is the answer that you are looking for.
Lee has a question.
So just to get back to Patrick's question, there's fewer disks at older ages, right? And so you can see that difference. At some point, the statistics are so low that it's hard, you know, if you have 1% or 5%, then the numbers are bad. Jesus, I wanted to ask you, so in the Orion multiple population thing, it would be surprising if there were no binaries, right? That would be like a particularly interesting population. Was your point here that the bright sequence had more fast rotators, and that's something you would expect if they had a bigger proportion of WTTSs? And that's why they're more likely to be binaries? Was that the idea?
Yes, basically this is the idea. In fact, most of these stars here are not classical Titaris, are mostly weak Titaris. I think I have only 2 or 3 classical Titaris here and 2 or 3 classical Titaris here. But the basic idea here is that fast rotator could have this radius inflation effect that can be that could change the luminosity and the color of the stars. So this is a similar result from the Pleiades, in which the faster rotator are located above the main population in the Pleiades.
Do we have questions? Do we have questions on Slack? No. Well, actually, I may have a question. Jesus is from. I remember from a long time ago that we had this problem when comparing the position of the stars in the HR diagram with predictions from evolutionary tracks. We have this problem that high mass and low mass don't necessarily have the same age. Do you still see that even with the improved addition of magnetic field and spots?
Yeah, well, I still have this problem that systematically in some models, the ages are different. If you consider different stellar masses. This is the problem is on here, and the problem with non-standard plots or a model like this summers is that you need to consider some spot coverage here to estimate as reliable age and masses. But this is difficult to get, and also the spot coverage can be different in different stellar mass range. So it's a real problem to estimate reliable ages and masses from this method. But well, it's a good proxy to do evolutionary model using differential ages.
Okay, thank you. We also have a question on Zoom from Marina. Oh, it's gone now.
Yeah, sure. So you're going back to the Bicari thing. So you are comparing group 1 and group 2. Have you got a chance to look at group 3?
Okay. Yeah. By simplicity, I don't consider the group 3 here because we have a small number. In fact, here is a small number, is only this small thing here. And when I do the selection and the cross correlation with the start with rotational period, I only have here that maybe the third population is correct. But yeah, it's difficult because we have a small number to study the third population.
Okay, let's thank again Jesus. And we move to the second invited talk of this session by Marina Kunka from Western Washington University.
Hello, and thank you for having me here today. Regrettably, I can't join you in person, but I hope you enjoy your time in Dublin. Especially after the last talk, the Orion complex needs no introduction additionally, but I still wanted to highlight just how large the entire structure is. That spans over 100 parsecs in the plane of sky. And if you don't know the distances to the individual populations, there is no reason to assume that width-wise it should be any less than that. Before Gaia, Lee and I have spent a considerable time trying to figure out its morphology, trying to estimate parallaxes and polar motions from a handful of stars using radio interferometry. Of course, since then, Gaia came out and made most of those efforts obsolete in that it provided astrometry not just for a handful of non-thermally emitting radio stars, but for billions of stars. And it allowed for detailed analysis on the star-by-star basis of trying to identify young populations through the HR diagrams, through similarity in kinematics, and allowed to trace back all these populations back in time, et cetera, et cetera. With Gaia towards Orion, it was possible to assemble quite a large census of pre-main sequence stars. There's something like 10,000 stars in here in total. The first takeaway is that Orion was much larger than was previously assumed. Not just Orion A and B molecular clouds, not just the Orion's belt or 25 Ori, but literally the entire constellation is littered with young stars from head to toe. As Jesus has mentioned, one of the very first discoveries that we had in Orion is that Lambda Ori had rather peculiar dynamics. that towards Lambda Ori, you do have this H alpha bubble, and young stars are perfectly embedded within that bubble, and they are all moving away from the center of the cluster quite fast with speeds of up to 5 kilometers per second. And they're moving ballistically. That is to say, the further they are from the center, the faster they are moving, such that they could be projected back toward the center at more or less the same age. And it has been theorized in the past that there used to be a supernova in Lambda Ori that has triggered the formation of some of these outlying stars. Therefore, such a ballistic expansion and correlation of that expansion with the H alpha bubble seems to signify that this type of kinematics, it could be interpreted as a signature of a supernova triggered star formation. But there is another H alpha bubble in this image as well, which is the Bernard's loop right over here. And if we were to look at the center of this bubble, somewhere over here, you can see that, well, first of all the stars are also perfectly embedded within this bubble, and they also appear to be expanding away from this imaginary central point in the plane of the sky, such that they can, most of them can be projected back toward the center with an age of approximately 6 million years. And it's not just expansion in the plane of the sky. As it has been mentioned, there are multiple populations that are projected along the same line site. And Orion D, which is a population that is located closer towards us, is moving towards us. And Orion C, which is located slightly further away from us, is moving away from us in the radial velocity space. And they are moving away from each other in such a way that at 6 million years ago, same age as the expansion traceback age in the plane of the sky, they would have been collocated at the same distance. So you have a forming of a three-dimensional bubble. And even the Orion Nebula, which is a cluster that many of us know and love, also seems to be moving away from the central point. So what likely has happened, or at the very least how I interpret the star formation history in this region, is that originally the entire Orion could have been something akin to a simple filament that 8 million years ago would have started forming stars. Probably 6 million years ago, one of those stars has died off, and it would have created a bubble around itself as a shockwave has interacted with the remaining molecular gas. That shockwave quickly compressed the gas and launched it into two different directions, here and here. In process, it triggered the formation of stars, triggered or accelerated it rather, quickly and rapidly dissipating the gas that is found in these populations. But the shockwave that got launched into the filament continued to go along and sweep more and more and more gas. And eventually it accumulated enough gas to allow the formation of the singularly most massive cluster that we have in the solar neighborhood. And indeed, when we were to look at, this was the model, this is the actual data that we have for the dynamical positions of all of the different stars in the Orion complex. They have been grouped together into the kinematically coherent populations. And you can see how the Orion complex has started forming and how has it evolved to the current state as all of the different groups pop into the existence at the age where they approximately are born. And you can see that the data roughly matches the simplified cartoon that I have drew for you on the previous slide. And in the Orion Nebula right over here, there's more that you can piece out. there has been a lot of controversy of the distance to the Orion Nebula over the years. But if you're to take the sources with which you have very precise Gaia parallaxes and separate out these sources on the basis of their age, you see that the distance isn't actually quite constant. That it's a very busy plot with a lot of different points, but just pay attention to the lines that are averages of all those points. That the oldest stars, they're found slightly closer towards us at a distance of approximately 385 parsecs. And the youngest stars, they are found slightly further away at approximately 395 parsecs. So you have a star formation that has propagated through the cluster by a considerable margin of approximately 10 parsecs. And going back to this model, this means that the older stars are found on the front side of the bubble, and the younger stars are found deeper within the filament. And the difference between the older and younger stars isn't radial velocity. That isn't to say that the stars themselves are accelerating over time or the gas is accelerating over time. Rather, it is something that is being pushed into the gas. It's the star forming front itself that is traveling through the gas. But more than distances, Orion Nebula has very peculiar dynamics as well. And over the years, the best conclusion that anyone could have is that dynamically, Orion Nebula is a mess. That if you look at the proper motions and the radial velocities of the cluster, it kind of looks like a very light cluster. But if you were to analyze the velocity a slightly different way, perhaps it has a slight preference towards expanding. So it's either virialized or it's expanding. It's definitely not contracting. Well, if it's expanding, is it bound or not? Well, we really kind of expect Orion Nebula to be bound because it is the most massive cluster that we have in the solar neighborhood. And if it's not bound, what else can we expect to be bound? Well, it still has gas. So maybe if it forms a few more stars, it will be able to reach the critical mass and perfectly stay bound. But then again, it's expanding right now, even with gas. So if it gets rid of all that gas, will it be able to stay bound after that point? And people were going back and forth, back and forth, back and forth, dating back decades. But now with Gaia and with our newfound abilities of measuring ages toward the stars, perhaps we can separate out the cluster into all sorts of different layers based on their age and based on their dynamics. And when we look at the sources that are moving towards the cluster, we see that they tend to be confined to this filament. So you don't really have sources that are moving toward the cluster from this side, from east or west. Rather, sources that are moving towards really are confined to the vicinity of the integral shape filament. On the other hand, if you're looking at the sources that are moving away from the cluster, well, there you have a slightly different morphology. You have a more spherical distribution of all the stars. And this doesn't really look like a cluster that is gently expanding, that is unable to hold onto its stars, and they're just drifting off every which way. This looks a bit more violent. And if you take all of these sources and you look at the radial velocities, you see that in almost all cases, the sources that are moving in toward the cluster center, their radial velocity distribution perfectly matches the velocity distribution of the molecular gas. But on the other hand, the sources that are moving away from the cluster center, not only do they have a wider velocity dispersion, which is particularly apparent here, but they also can be slightly offset from the gas, which suggests that the formation mechanisms for both the stars that are moving towards the center and the stars that are moving away from the center is slightly different, in that the stars that are moving towards they're still infalling and that they probably still have more primordial velocities, whereas the stars that are moving away have been dynamically processed in some way. And well, one way in which you could dynamically process a star is if you have a triple body interaction and if you were to inject one star from a cluster. And to date, several dozens of runaways have been identified near the ONC. Most of them trace back directly towards the cluster center. And for the most part, these runaways that have been identified in the past have been pretty fast moving with speeds of over 10 kilometers per second, and some with speeds over 30 kilometers per second. And to eject these stars, all you need is either a newly formed unstable triple system, or you just need to pack a lot of stars in a very, very dense cluster and have a couple of them happen to pass by one another, especially if you have a very massive star in there. But these runaways moving with such large speeds, they are nothing more than the tip of the iceberg. That you would expect most of these ejection encounters to have much lower velocity, something in the order of 2 to 3 kilometers per second. And so it stands to reason that this expansion signature that we see is from these unstable triple body interactions within a very dense cluster, the core of the ONC. Whereas the sources that are moving towards the cluster center, well, they are being pulled in towards the very mass cluster through gravity. So you have different processes that are governing the dynamics of both of these sets of stars. And the only interpretation that I could come up with is that the cluster is most likely bound, but it is probably not virialized because all of these stars, they're still too young. They're still forming and the cluster is just not young enough to be virialized. So when you're measuring a virial parameter for a young cluster, it could be overestimated just because the cluster hasn't settled yet. But in addition to the infall and to the addition to the expansion, you have a third direction of motion, which is rotation. The stars could preferentially move tangentially with respect to the cluster center. And some stars, they are moving clockwise in pink, and some stars are moving counterclockwise in green. And you can look at all of these stars and you can count how many stars are moving which way at a given age bin. And interestingly enough, there is some angular momentum evolution as a function of age, that at the older ages for the stars over 2 million years old, the stars that are moving clockwise are matched by the stars that are moving counterclockwise in numbers. But once you get to the younger ages, younger than 2 million years, you definitely have a preferred direction of motion that most stars, they're moving clockwise, and there are relatively few that are moving counterclockwise. So as the cluster is aging and it's actually starting to grow massive enough to develop a cluster, you are probably developing sufficient angular momentum to sustain organized rotation. So Orion Nebula is certainly a very wonderful cluster that has a great deal to teach us in terms of how clusters are forming and how they're developing dynamically in time. And it certainly has been a favorite cluster for many, and people have studied it for decades, and they have developed very pristine membership catalogs of this region. And we have all sorts of data towards the cluster, such as radial velocity, such as kinematics of the gas. But even if we didn't have membership catalogs nowadays in the age of Gaia, the members of the Orion are pretty easy to find because you have low mass pre-main sequence stars. They stand out quite clearly on the HR diagram against the main sequence stars and against the red giant branch. You certainly would have considerable amount of contamination once you get closer and closer towards the high mass end. So certainly those catalogs wouldn't necessarily be as comprehensive as the catalogs of members that we currently have, but you can get a fairly clean catalog, even just selecting sources in this parameter space. But what if you wanted to move beyond just a single cluster or a single star forming region? What if you wanted to select young stars across the entire sky along the HR diagram? Well, it's starting to become a bit more complicated because you are starting to average different populations of different age. And the older they are, the closer they get to the main sequence, so you no longer have such a nice separation between them. And if you are starting to look at larger distances, you have all of these horrible red giants that get scattered into the parameter space of wonderful young stars. So you are going to have a more contaminated catalog if you're trying to make some sort of automatic cuts. And alternatively, you probably could scrutinize each and every star, but the catalog that Gaia produces is so large that you would need to have an infinite amount of time to construct a clean catalog if you were to do it by hand. There are still some ways that you have to select pre-main sequence stars. First of all, you can turn towards clustering. Gaia provides a rather good catalog of parallaxes and promotions, and you can take advantage of the fact that the young stars, when they're forming, they're dynamically cold. They seem to be collocated in the same volume space, moving with the same velocity. And you can identify all sorts of different moving groups in the Gaia catalog. And that has been a fairly fruitful endeavor. There are currently more than 8,000 moving groups known within 3 kiloparsecs. Some of them are young, some of them are old, but you can estimate their ages through isochron fitting, since presumably most stars within a moving group has formed more or less at the same time. And you can see how in red you have young populations with a sizable pre-main sequence stars that get closer and closer towards the main sequence as they age. And then after approximately 100 million years, you have high mass stars starting to die off, and you have a rather nice turnoff. And you can estimate the ages of all of these moving groups, and you can scrutinize them. You can estimate their velocity dispersion, how they evolve over time. The overall morphology of these moving groups should come no surprise to the people in the star formation community, is that they tend to be string-like, resembling the morphology of the filamentary matter clouds from which stars form. And these string-like populations, they are really ubiquitous among young stars. On the older end, as they age, their morphology becomes a bit messier. Many more of them end up being more compact, more cluster-like. But with some poking at the data, it's possible to find these residual strings even at rather advanced ages of close to a giga-year. But you wouldn't necessarily be able to find all of the stars that you're finding interesting through clustering. For example, you certainly wouldn't be able to find runaways through clustering because you're assuming that all of the stars in the population should have the same velocity. And runaways have been dynamically processed. They no longer have the same velocity as the parent population which has produced them. So you can try something different there. And what's nice about the clustering catalog is that it allowed us to assemble a rather clean catalog of the pre-main sequence stars across the entire sky. And we can turn the data volume from a hindrance to the advantage in that you can feed the photometry of all of these pre-main sequence stars to a computer, and you can train a neural network trying to teach it to identify pre-main sequence stars, even if they're not necessarily a part of a moving group. And to make a long story short, this was the result of such a training. Here we have a binary classification of how likely a particular star is to be pre-main sequence or not. And the neural network has been able to figure out that stars over here are quite likely to be pre-main sequence, whereas stars over here are not. And the classification is really done on the source-by-source basis, using a multidimensional photometry more than you would normally be able to use when you're trying to do isochron fitting. And not just the binary probability of whether a star is young or not, you can also empirically estimate the ages of the stars based on the average age on the population in which these stars are found, used as a training set. And the neural network is able to figure out that the stars furthest away from the main sequence are quite likely to be very young, and the stars closer towards it likely to be somewhat older. And here you can see how different thresholds in our confidence level changes the types of the population that we select. At high threshold of over 90%, we have a rather clean catalog that is very carefully avoids both the main sequence and the binary sequence, as well as the red giant branch. On the other hand, at the lower threshold, you get closer and more into the binary sequence, and you do have more contamination from the red giants, but you are also able to select out a few more slightly older stars. So it really depends on what ages and what certainty levels that you need to select out and study a particular population. And so let's go on a brief tour of the solar neighborhood. Here we're looking at the stars younger than 2 million years, which should be a fairly familiar hunting ground for many. So we're seeing the Orion A and B molecular cloud, row of Ophiuchus, Taurus, and Perseus, and several other regions. And as a reminder to most of you that these regions appear to be located at slightly odd angle with respect to the galactic plane. They are tilted by approximately 20 degrees, and this has been historically referred to as the Gould's belt. Now, at the ages of 2 to 5 million years, we're starting to get more of the Orion complex. We're starting to get more of Upper Sco. We're getting some of the more distant populations, NGC 2264 and Cygnus OB2.
You have 5 minutes left.
Yep, thank you. At 5 to 10 million years, we're starting to have Vela, which is starting to become a bit more popular in the last decade or so, but very little of it has been known before the last decade. You're starting to get Cepheus, and that is a very, very messy region because it contains a lot of very small star-forming regions. 10 to 16 million years, you're getting the older bit of SCO-SEN OB association. 16 to 25 million years. And at the ages older than 25 million years, you are starting to venture into terra incognita. That is to say, these stars are a bit too old for the star formation community to have looked at before in the past, certainly in any type of organized manner. And these populations are still a bit too dispersed, too large, still trace too much of the molecular clouds that would have been there back in the day for the people who study more about clusters to take a note of. And if we were to take all of these young stars and to plot them in the top-down view of the Milky Way, of the solar neighborhood, where the sun is at the center and galactic center is to the right, there are some populations that you would recognize: Taurus, SCO-SEN, Orion, and several others. But there are a few interesting features that become apparent in this map. First of all, Taurus and SCO-SEN appear to be connected via a complete ring of stars that is primarily traced by the older populations such as Alpha Per, or alternatively known as Cas Tau OB association, as well as some of the older stars towards Vela. And then after a slight gap, you have a lot of other suspiciously equidistant star-forming regions. And it may seem a bit odd why you would have all of these different rings, why the sun would be at the center of this ring. But well, the sun is found at the center of the local bubble, which is a cavity in the interstellar medium. And you can trace the local bubble using both diffuse interstellar bands, which trace X-ray emission, and using various dust tracers as well. And you can see the region where the local bubble ends is pretty much precisely where you're starting to get this ring of stars. And you don't really have any star-forming regions within 100 parsecs, other than something very low mass, such as TW Hydra.
You have 2 minutes left.
And again, because you have most of these young stars are forming together the Gould's belt, it stands to reason to assume that the formation of the local bubble and the Gould's belt could potentially be related. And to preempt the question, followed by the following talk, which I would assume will talk a bit about the Radcliffe wave. I don't believe that the Gould's belt and the Radcliffe wave are exclusive to one another. Rather, it's probably these bubbles that are driving the ripples in the wave. But, and this bubble really is expanding. That we don't have many radial velocities so far, but of the radial velocities that we do see, they seem to be moving away from the center of the bubble, and the velocity of these candidate young stars is really quite different from the radial velocities of the field stars. But going back to the place where we started, going back to Orion, if we're to take this catalog of stars and look how all the stars in Orion, near the vicinity of Orion, are moving, all of the stars in Orion itself are expanding away from the center, as I've mentioned before, most likely from a supernova or from potentially some alternative, more competitive explanations, which I'm not aware of. But all of the stars in the other star-forming regions, they really are moving towards Orion. And it's hard to explain such a motion through anything else other than gravity. And we're still arguing with Lee about it, but hopefully I would be able to convince him sooner or later. So to summarize, originally I was quite ambitious and I was hoping to talk about more star-forming regions other than Orion, but its gravity is such that it kept pulling me back in for more. But it's needless to say that all star-forming regions have a very unique star-forming history, and that the types of kinematics and the types of history that you can trace via kinematics is very unique. And often you need to look at all sorts of different scales. The structure on the large scale can drive the kinematics on the smaller scales and vice versa. And now in the era of Gaia, we do have a lot of data with which we can analyze the histories of all of these star-forming regions, and even more so in the next 5 or 10 years once we start to get more and more radial velocities for all of these stars. Thank you.
So we have a question on Slack, or okay, we can start with Jan Bonnel.
Thanks, Marina. That was a fantastic talk. Curious about the ONC, the difference in the infalling filamentary stars and the ones that are expanding. Do you see any difference in their properties, in their masses or ages or anything like that?
Not really. Well, there is some difference in distance, and there's some difference in the overall distribution in the plane of the sky, so that the younger stars, they really tend to be concentrated in the center, in the core of the cluster. Originally, star formation was occurring everywhere throughout the filament, but as they age, you have more and more self-gravity, so everything gets pulled in more towards the center. But in terms of the expansion itself is really dominant in the older stars that are still kind of forming the filament, because at the younger stars, you primarily are concentrated here. At the younger stars, you may have slightly faster ejection velocities, but that's more due to our targeting, because as the stars age, they would eventually move out of the map of what we consider to be ONC, and we may not necessarily be able to trace them currently within the map of the survey. But yeah.
Is there any indication that they may be lower mass, the ones that are expanding?
We haven't measured their masses, but I don't think there are many obvious differences.
Okay, thank you.
So we have a question from Zoom from Hans, if you want to unmute.
Yeah. Can you hear me? Can you hear me?
Yes, we can hear you.
Oh, well, that was a very interesting talk. What a tour de force. Thank you so much. 2 questions, or maybe even 3. The first one was, will you present these results at the Protostars and Planets 7 as a chapter? Question number 1.
We are presenting something for Protostars and Planets, but not specifically this result.
That's a shame. That should have been in there.
Second
question is about.
Yeah, we're just finishing up the draft of the paper, so it wouldn't have made it for the Protostars and Planets, unfortunately, in time.
Second question about binarity. I mean, there are the works, the old works actually by Rainer Köhler and by Monika Peter about the binarity changing as a function of a distance from the ONC cluster center. I don't know whether you have any comments on that. And in the same spirit, I mean, we had heard from Jesus and now from you about these different populations and the Beccari and Herapova studies about different ages. Do you agree with the different ages, or do you more favor the interpretation that Jesus has given us, that it's not the age, but it's something else that's different?
So it's kind of yes and no. So there are different stars of different ages. You do have a prolonged period of star formation. You obviously do have some binaries there as well, but the bulk of what they see of different spatial distribution as a function of age in the cluster is real, in that you do have more young stars are located within the center of the cluster, and more expanded distribution of stars at the older ages. But I don't necessarily think that they are discrete populations. You have a more continuous evolution of ages within the cluster. Regarding binaries, that's a very, very, very deep can of worms, in that I don't think, especially in Orion, there are arguments that the multiplicity fraction is not necessarily a universal thing. And in the past, we have found that in the denser environments, perhaps not in the center of the ONC, but just on the outskirts of the ONC, you have a high, wide binary fraction than you have in the more diffuse regions, which is opposite of what you would expect through dynamical processing. And there is a poster by Matt DeFurio, which is also very interesting, in that you do get a very high multiplicity fraction in the ONC of brown dwarfs. So there are a lot of forms that are very difficult to get to in a quick period of time.
And there are the triple stars.
Maybe we can Hans, maybe.
You talk to Pavel Krupa?
What about him?
Yeah, because he's studying.
Okay, Hans, we need to move on to next. We have time for maybe just a last question. I know Lee was raising his hand. Thanks.
Hans, you'll have to ask. Anyway, I just wanted to say, in terms of Marina's can of worms, although they're wriggling, you know, that second sequence is exactly where you would have the binaries.
Yes.
So it has to be some binaries.
Yes,
and
there are some binaries in their sample.
You know, so it's just a question of proportion.
Mm-hmm.
Okay, so let's thank Marina again. And move on now to two contributed talks. The first one by Joao Alves from the University of Vienna.
Thank you for the opportunity. This is a brief report on all the things we're doing here regarding Gaia and how I think Gaia is really changing the field. This is work done by all these people. I want to call attention for Catherine Zucker has been fundamental here, and we just have a new professor in Vienna called Alvaro Akar. So another reason for you to come to Vienna. Oh, okay. So let me start to the very beginning. This is my homage to Lee. I was a very young PhD student. I just finished my master's thesis, and I found this little blip that you can see here, little star that becomes a very bright star. And Lee, this is my second paper, and Lee played a fundamental role in this paper, and I learned immensely from being at the CF at that time. I learned immensely from Lee. I never told him that. He's an inspiring figure, and I love this picture by Javier because I think he captures very well for me what Lee is. Every time he starts doodling, you better pay attention. Thank you, Lee. Good. That out of the way. Oh, not yet. Here's our friend Lee and Andy and Phil in Andy's office. And what I believe Andy's pointing to, maybe that's the original square, but no, Bonner-Ebert square, whatever that thing was. Anyway, I also like very much the look on Lee's face because it reminds me of the look of Lee's face on his webpage. And you know, he's cooking something, and it's great, great look. So my brief outline: how is gas distributed around the sun? Our efforts to start measuring the 3D motion of the ISM, and what is a cluster? Gould's belt, we all know how it started by Gould 150 years ago. We noticed this river of blue stars, and it looked like there's a ring around the sun. Eventually, it was not just stars, it was gas, and we build up models such as this one, where we believe that you know, there's this circle, this ring of clouds and star-forming regions around the sun, and it's expanding or not. I mean, it was never very clear. This idea of the Gould's belt was then crystallized by the Parkes mission and by the work of Tim DeZeus and others, where it became very apparent that there is some kind of special distribution of not only star-forming regions of young stars, but also dust. And this is perhaps best visualized here on the right. This is the distribution in Cartesian coordinates, so galactic center always in that direction, direction of motion always in that direction, and this is Z. Where you could see, this is the OB stars from Hipparchus. You see there's some kind of structure here. Looks like it could be a ring that's inclined about 20 degrees from the plane. Several models. This is from 1952 already until now. No time to go through them, but none of them completely satisfactory. What we wanted to do then is, well, why don't you just measure it, and using a 3D dust mapping to figure out what exactly is the Gould's belt. How are we going to do that? We're going to do that by doing essentially a Wolff's method, modified Wolff's method, where we're just going to plot the number for a certain direction, there's a pixel in the sky. We're going to plot the distance versus the extinction. And of course, when you suddenly at some distance hit the cloud, then you have a wall of extinction, and you try your best to figure out where is the wall starting, and that's the distance to your cloud. Now, this is before Gaia, and this is where the magic starts, is that you go from things that have errors about 10 to 30% to things that have errors about 5%. This is before Gaia and after Gaia. And here's other regions before Gaia, and then after Gaia. Look at how well defined then that wall of extinction is. And that is then what we're going to use to measure distance to clouds. How good is this measurement? Here's the comparison between the dust distances. And here's the masers, which are the benchmark for distances in the galaxy. This is well established. This is a work of Mark Reed. And we're going to use them, and we find that it's essentially a one-to-one relation. So they agree to within 10%, and there's really no systematic offset, at least out to 2.5 kiloparsecs. What that means is that suddenly we don't need masers anymore to determine accurate distances to clouds. In fact, all you need is a direction where you have dust and measurable stellar properties. This is quite something. This is quite a jump. Okay, so this is how we do it. Let's do it. Here's the anti-center. Here's the clouds that Lee and all of us love so much. Here's Taurus, Orion, Perseus. These are the beams. So this is the directions to which we're going to determine distances. We're fairly confident in the method. We can go for very low column densities in between what we call this, well, the complexes. And when you have galactic longitude, galactic latitude, and the distance, you can convert to Cartesian coordinates, and you got this. You get this. So here's the sun, here's Orion, here's Taurus, Perseus, and this is very, very interesting and very, very unexpected. Completely correlated distribution of all the star-forming regions, essentially, that we've been working all our lives on. They're basically divided in two main families. What you see in the background is a 3D map or a projection of a 2D map from Greg Green. There's two families of clouds, of star-forming regions. There's this one that we call the Radcliffe wave, and then this one that Rosine Landman calls the split. It includes, of course, Serpens, Aquila, and Scosan. Okay, if you look from this end, it's like a planar structure, and if you look from orthogonal to it, it's a wave. It's an attenuated wave. I don't have a lot of talk to explain or the ideas that are behind this, but it is definitely there, and I think it explains a lot of what we used to call, I think what I used to call the Gould's belt. What you have here is the ring, and then suddenly you realize, well, maybe it's not a ring, is this structure here called the Radcliffe wave, and then the split. There's essentially two structures, not really a ring. What about the inclination? Well, the inclination is just, the scales are not the same. It's just when the wave crosses the plane, this is what you're catching up in the OB stars. The same thing on this projection. So here's again the sun, the split, and the paper by 2018 using Gaia data, and this is modeling the Gould's belt. So here's proof that the Gould's belt supposedly is expanding, and what we think it's happening is just that these points here belong to the Radcliffe wave, belongs to the split, and these others belong to the split. So what you're seeing is these two structures moving away and creating this, I guess, illusion that there is an expanding ring. I could go quickly, but I can show you a 3D model. This is in a paper, but I don't have the time. Ask me in the end if you want to know. So what's the new local neighborhood then if there's no Radcliffe, no Gould's belt? Well, it starts in somewhere in CMA, in Canis Major over there, on 1.2 kiloparsecs away. Then you go down to Orion, and then look at the left, and there's Perseus very close to us, Perseus, Taurus, even a California nebula. Then you go up to Cepheus, and then you go down to Cygnus, and Cygnus X. Probably will continue. We don't know that, we don't have the Gaia as an optical telescope. When it gets close to the plane, then you don't really can say much. So there's one main structure here, the Radcliffe wave, and there's another one, but it starts with these leftovers of the formation of Scosan, Corona, Chameleon, Lupus, even of Fucus. And then there's the other structure that we just saw before, which is a split, which includes Ophiuchus, Serpens, and Aquila. And this is it for the local structure. We don't really see a Gould's belt in the sense that it's not really connected. What you were seeing, we argue, is just two structures in projection. Wait a minute, how do you get this 3 kiloparsec linear structure? We don't know anything like that in other galaxies. Actually, we do. And I learned this, and it's pointed to me by Mark Reed, is that the spiral arms that we love to fit spirals and log spirals to turn out to be segmented spirals. So there's a segment here, there's a segment there, there's all these segments around here. And I think what the Radcliffe wave is essentially just the local arm, and it's just the gas reservoir of the local arm. And if that's true, then we should expect a lot of B stars only to one side of the Gould's belt of the Radcliffe wave. My God, Freudian sleep. Wouldn't it be amazing if we can measure this whole thing in motion? And this is what we're trying to do. We have a large program, a public survey at ESO, where we're mapping all the nearby regions within 500 parsecs. And the idea there, apart from a lot of science formation cases from IMF, from disks, from everything, is to use these guys, the most embedded objects inside the nearby clouds and measure their proper motion. So of course, we've been observing them for the last 4 years. We have every 6 months, we observe all these clouds, and we want to measure the proper motion of all these sources. The results are coming soon. You should, if anyone is interested, please contact me. Here's Ophiuchus, just one field in Ophiuchus, this one on 1688 and this 1688 at sub-arcsecond resolution. And you can see all kinds of disk structures here. And what's for me fantastic is this wave-like or blown-like or castle in the sand-like structure that you see even inside L1688. Lots to talk here, but I'll move on. Now I want to tell you about a pilot study, because we can already do that with Gaia. And this is done work by Josefa Gostschädel's thesis, where she figured out first, but just by using Gaia and the positions of the YSOs, that Orion A is really not on the plane of the sky. This is just the only part of the plane of the sky. This is the ISF, the sun in this direction. Most of the cloud, almost along the line of sight, 70 degrees, and 90 parsecs instead of 40. One thing that was curious, why is this bent? Why is this filament bent exactly where the ISF is? We suspected that to do with feedback from a previous generation of stars. And this is what Josefa did. She uses then the YSOs embedded in nearby clouds in Orion, in the Orion complex, and uses them to, determines if there's no radial velocity, uses the radial velocity of the gas. She has to guarantee that the stars are embedded, and she can construct movies like this one. What you're seeing here is a slide. Let me just jump. Sorry, I made maybe this way is better. Here's your Orion, and the sizes. She just divided Orion A, Orion B, and the nearby outlying clouds into sections, and the size of the symbols here is distance. So you see that the Witch Nebula, which is this thing here, is very close to us. That's the Orion, the ISF, and that's the tail of Orion fading down, and this is fading away from us. This is Orion B. This is, if you look at it from ZY, so galactic center to our back, and this is just to tell you that we're going to take some center, because we're going to move this point back in time, and we will figure out, this is X and Y.
You have 2 minutes left.
All right, so I'll go just straight to the movie. And what you have is that we have the clouds consistently moving away from some center, and I'll repeat this. These first clouds here are the ISF that we've been talking a lot for a long time here in this conference. And notice how the ISF has clearly been pushed by something, because it's going to overrun the tail of the Orion A in about 7 million years. So we can already start doing this. I want to end up with another line of work we're doing here in Vienna, which is figuring out how exactly go from clusters to the field population. This is work by Stefan Meingast. And here's the first thing that Stefan found, is this very strange distribution of stars. They are coeval. They have 120 million years. They're just like the Pleiades, but they are a different kind of Pleiades. Now we're seeing X, Y, and Z in Cartesian. They look like almost submarines or pancakes. And this is kind of the first of, I think, many that are coming now in the literature, just one last week, I think. This is work by another student here in Vienna, where he took the original data set and machine learning managed to get 10 times more sources on it. Another, using the same techniques, then Stefan found out that what we normally call the nearby open clusters, especially the younger ones, and this is 2516, we're seeing a 2-degree field of view here, 10 and 60. This is a cluster. This is now work for Cantat-Gaudin, defining with Gaia data. And what Stefan found is that they're really not round. They're, at the 10 degrees, there's the longer elongated. You have to go for 60 degrees to capture the entire cluster. So this is sources that are close to the Earth. So there's perspective effect. This is further away from us. What we thought was a nice roundish cluster turned out to be enormous structure, cigar shape like, and Stefan calls this the halos of these nearby clusters. It is not one. Out of 10 nearby ones, all of them have a corona except for the Pleiades, for whatever reason. Pleiades is this one here. They all have a core that we used to see before and know very well, but now we have more stars in the corona than we have in the cores of these clusters. This has to do surely with the initial conditions, has to do surely with the galaxy. So my final thoughts, Gould's belt, I think, is a projection effect. The nearby star-forming clouds are not random distribution, are highly correlated. There are two families of clouds, so the mothers of the GMCs, so to say, which is very important for particularly following the work of Lee on forming molecular clouds through flows. I think this is exactly what we have to focus on to understand the gravitational wave, and I think this will give us a wonderful handle on not only our galactic structure, but also on how you form these clouds. 3D motion is coming soon, and we have to go back to the drawing board. I don't know exactly what a cluster, like I don't know what is a core anymore, or a stream. I think this is a very exciting time to work with Gaia data in star formation. So I thank you very much.
So we will have time for 1 or 2 questions max in the room. Yes.
Thank you for the very nice talk. I'm really surprised about the gold belt, that it's just a projection effect. I'm wondering that you showed how that Gaia can actually, we can constrain the distances through the extinction. So, but as we further move on in the line of sight, the extinction keeps increasing. So how do you know the width of the clouds, especially the gold belts? Is it just through star clustering within that region and the parallax, or do you also see some velocity of gas?
So the increase you're talking about is really, really tiny. So you see my screen? See my slide? No, you don't, because I stopped sharing. So what we're seeing is the increase you're talking about is this almost not there. So for the local clouds, you're very good at determining distances. That's why you cannot go with this method to the end of the galaxy, because you will have that problem you're talking about. So with what we're detecting here also is the wall of extinction. So we don't measure really the depth of the structures, but you can see this is in the paper that you can, we're touching the first surface of the clouds, but at this scales, the clouds are tiny. So we're not making any statements, okay, here, because we have enough points to say that it's Orion A, Orion B, whatever. We don't make statements about the width of the clouds. For that, you want to go to the 3D dust maps from Greg Green and Rosine Lalman.
All right. Okay, thank you.
Another question on Slack? No. So Jan has a question.
Thanks, Joao. A question about your corona. Can you tell anything about the kinematics between the corona and the cores? Is there a way of kind of giving you like effectively a tidal radius of the clusters or something like that from there?
Yeah, there is. It's just that we don't have the data. We're waiting for the 30 million radial velocities coming from Gaia next year. Yeah, so we have these huge populations of stars that we believe belong to the clusters. A lot of them are totally unknown and unstudied. We don't have surveys on top of them and all that. And this is the big change that's coming next year.
Thanks.
Okay, so let's thank Joao again.
Thank you. Bye-bye.
And we move to the last talk of this session by Vito Squicciarini from INAF, University of Padua.
So hi everybody, and thanks for giving me this opportunity. My name is Vito Squicciarini. I'm a PhD student at the University of Padua in Italy. And today I will talk about the episodic star formation in the upper Scorpius association recognized by its kinematics. Just to give a brief overview, the Milky Way, as we know, is a living environment. It is a galaxy that is still forming stars. So in a sense, we can see the process in real time. And we also see that while during the first million years, most of the stars are embedded in the parent cloud, after, let's say, 10 million years, the vast majority of the stars have already been ejected in the field. So we can say that most key processes like star formation or planet formation or the dispersal of the original cloud or the birth, the evolution, and the final disappearance of the protoplanetary disk happen in between in this time window. And in particular, there are some structures that can manage to survive a little longer. And we can see this structure that are association and open clusters for some tens or hundreds of million years, but they are bound to be destroyed by the galactic vital field. But we think that associations in particular are really interesting to study the problem of evolution from the original clouds to the final group of stars, because associations are young system, of course, and they are also sparse, meaning that the density is very low. You can see it in the box. And this implies that the interaction among the stars are negligible. So we can neglect the close encounters and the scattering between stars. And this is a very important assumption. And please keep it in mind because it will be the key for everything that I will tell you after. So association, an ideal benchmark to study star formation from a kinematical point of view. Just to have a practical idea, we focused on a case study that is Corpus Centaurus. It is the nearest association to the Sun with a distance of about 140 parsecs. And it has an age of less than 20 million years with a lot of spatial variations. And it is classically divided into three groups that are Upper Scorpius, Upper Centaurus Lupus, and the Lower Centaurus Crux. But you can see on the left that there's a huge problem when studying an association like this one, that it spans a huge area in the sky. In this case, the spanned area is about 80 times 40 degrees. And so you can see that there are a few thousands of real members, but they are in a sea of hundreds of thousands of not members. So the key problem is that we need a method to disentangle real members from field interlopers. So the basic assumption is that we use proper motion that distinguish the motion of an association from the field. And this is what limited the traditional studies. You can see here that the classical study by Blow of 1964 that was not overcome for 30 years basically had found just 77 stars in the whole association. They were all B stars. And the first revolution came with the purpose that led to, we can say, proving almost down to one solar mass. And you can see that there's a catalog of sources of 1999 of about 500 members. But the real revolution, as we are saying a lot of times in these talks, came with Gaia, because Gaia gave us the opportunity, as you can see on the left, to prove all the mass, all the initial mass function down to the deuterium burning limit. And the more recent catalog based on Gaia DR2 of this association comprises some 10,000 of real members. So here it is, the catalog on the right by Damiani et al. And you can see that we have now an expanded, a complete census of the association members. And we also have precise distances thanks to Gaia. So we have the absolute magnitudes of these stars, and we really have the possibility to explore both the initial mass function and the star-formation history. But with Gaia, we can do even more, because this that I show on the right is just a snapshot taking time. It's a snapshot taken at present time. But of course, the stars have an history. And so we are interested in seeing how these stars were arranged in the past. And under the assumption of negligible interaction that I was mentioning before, we can think of rewinding the tape using present position and velocities to see where they were found some million years ago. So we started from the position and the velocities, the proper motions from the Gaia early DR3, and we put them together with the radial velocity from Apogee and Gala. So we built a catalog with a full knowledge of the 6-dimensional phase space, about 30% of the sources. And so we were able to perform a full 3D kinematic reconstruction of the motion of individual stars that are the points that you see on the right. For the 70% of the sample, we don't have the velocities, but we can still do a 2D reconstruction and correct for the relative motion from the sun to the association, thanks to the 6D sample. The animation that you see on the right is actually related to Upper Scorpius. That is a subgroup of Scosen that was the real target of our studies at the end. It is the youngest region of the Scosen, and it has a projected density that is varying especially. And so we performed the same kind of analysis. You can see 2D projection in the right. So these are alpha and delta. And you can see that going backwards in time, there are moments in the past in which the configuration of the stars was tighter than nowadays. And so in this way, we could identify 8 subgroups within Upper Scorpius that had a more compact configuration in the past. And the interesting part is that if we put together these subgroups, we build a clustered component that is distinct from a diffuse component. So just to give some numbers, we have 2,500 of stars. About half of them are in the diffuse population, meaning that they can't be traced back to a subgroup. They don't show any sign to having been more clustered in the past. And our idea was that the initial state of the diffuse component has been eroded by the galactic tidal field. But if this is the case, we expect that there is a difference in age between the clustered and the diffuse component to explain this erosion. And so we verified using, again, Gaia distances and the photometry from Gaia and to mass, using a tool, MADIS, that we're about to publish, that the ages that we derive for the clustered component is different and is younger than the age of the diffuse component. And this is really reassuring in a sense, because the distinction between the two was based on a purely kinematic basis. And then here we go to disk that are one of the main topics of this conference. And we thought of using disk in a different way from the usual way that we study disks. We know that Upper Scorpius is so young that it should have a lot of stars with primordial disks. And we also know that statistically, the number of stars within a population that still bears a primordial disk is a function of time. It is an exponential function. So if we assume a time scale for the decrease of the number of disks in a population, we can get an idea of its age, measuring the fraction of stars that still bear a primordial disk. And so in this way, we built another another time estimate for each of our subgroups. And you can see on the right that this cage is in good agreement with the isochronal age estimates. And so, in a sense, we had another independent confirmation that the age spread is real, because we see that the disk fraction in upper Scorpius is higher from this clustered than in the diffuse component. And you can see in the lower corner, lower left corner, one of the subgroups in which we divided the diskless and the disk-bearing stars in red. The problem is that we tried to compute the ages also in a kinematic way, that is using the moment of maximum spatial coherence as an age estimate itself for each subgroup. But we saw that the kinematic age derived in this way is always an underestimate compared with the disk age and the isochronal ages. And so we think that it can be related to the time scale of gas dispersal, because when we trace back the stars to their the place where they were born, at some point there will be gas, and so the assumption of having a uniform motion will break down at some point. So just to conclude my talk, we could identify that this association, this young association, had an episodic star formation history with some hundreds of stars that were born independently in each episode. And the combination of kinematics and photometry and also the presence of disks can really help shedding light into the star formation history of the young association. And here I'm done. Thanks for your attention, and I'm happy to answer to your questions.
Thanks a lot, Vito. Are there any questions in the room? Lee?
So just a general comment on the last set of talks. You know, it seems to me that there must have been multiple supernovae going off in the region over a 10, 20 million year period. And I wonder if that affects, the sources should be separated, right? That you have these explosions that will not be all exactly in the same place, and that will distribute things and make it complicated. And I wonder if that has any relationship, as talking to the current speaker, to your problem with kinematic ages, where there could be different dispersal times because you had multiple events.
Okay, thanks for the question. Actually, there is this hypothesis that the whole upper Scorpius that is younger than the other parts of the sun. Here I show you the graph here. Upper Scorpius is younger than upper Centaurus lupus and lower Centaurus lupus, and there is the hypothesis in the literature that it is really due to feedback from supernovae explosion. So, in a sense, taken from the big perspective, the whole upper Scorpius can really have been under the feedback of a supernovae. In my problem that is in the subgroups, I'm not really capable of answering your question. I don't know, probably there have been some supernovae because we have a 10 million years structure, so they can probably have started some of the most recent formation episodes, but in our studies, we didn't test it in any way, but
Sure.
It's really interesting.
Yeah, no, I mean, this is more of a comment, but it's just that studies by like de Avelege and Breitschfort, argued that the local bubble needed like a dozen supernovae to go off. And it's just that sometimes, if you have a really large structure, it's hard to make that with even multiple sources all from one position, that it helps to spread them out in some volume, and that helps you make a bigger bubble. And sometimes I think that's what you need.
Thank you.
Okay, is there any other question on the, I saw there was a comment by Joao, I think, on the Slack. Okay. Enrique?
Hi, Vito. This is Enrique Vasquez Madeni. Very interesting talk. This is just a comment that the structures that you seem to be finding and all this substructuring seems very consistent with the, well, it gave me the impression that it's very consistent with this hierarchical structuring of the gas. And so I would like to hear your comments on whether there's any conclusions that you may have concerning what was the structures, the molecular cloud structures where these stellar structures came from. And also maybe I'll send you an email about what we have been seeing in the simulations, but can you infer anything about the parent structures, so the gaseous structures where these stellar structures came from?
Thank you for the question. I'm waiting for your email then. I'm not able to actually to answer about it because I'm not an expert on gas. I just traced back the kinematics. But as you said, the fact that we see some small structures seems to argue for some small concentration of gas. So in a sense, on a hierarchical structuring of the gas, but this is more of a kind of an intuition because we didn't have a way to connect it with the presence of gas that is no more there. So I think that it is interesting to connect it with the studies in younger regions. Like for example, there's the Rho-Fuki cloud within Upper Scorpius, and the Rho-Fuki cloud itself still has a lot of gas and dust. And there have been some studies that show, for example, that the stars in them, that the stars are older than their kinematic ages, something similar that I've shown you here. And in that case, there is still some gas. So I'm really convinced that there's a strong connection, but I don't have the means to answer it because I'm not an expert in gas.
Okay, okay, thank you.
Okay, so we thank Vito and all the speakers for from this morning session again.